Gabby will speak for, present her thesis for approximately 40 minutes. After that, we'll have a period of questions. I will ask that the committee members not ask questions during this period, because after that, about 1 hour from now, committee members, we will go up to the Admiral's Conference Room, which if you don't know where it is in this building, I'll show you where it is. We'll go up, we'll have an opportunity to ask Gabby questions up there. Then we will send Gabby out, and afterwards we will tell her what our comments are and the result of things. So with that, I will turn it over to Gabby for her doctoral.
Okay, wonderful. Thank you so much, Kim, and thank you to all of you for being here today. I'm really excited to tell you about what I've been working on for the last 5 years. So without further ado, we're going to be talking about coral reef monitoring with machine learning and remote sensing. Owen!
You look into Zoom, you just have to move back here.
Oh! Thank God you're here. Okay, if you've ever attended a talk on coral reefs, you know that we have to start with the bad news first. And that is that half of the world's living corals have been lost since the 1950s. And more recently, in April of 2024, we saw the 4th ever global bleaching event. About 84% of the world's coral reefs were affected, and about 83 countries and territories reported bleaching of their corals. But the statistic on this slide that I think is the most shocking is that 3 out of 4 of these mass bleaching events have occurred since 2020. But why do we care about corals? Well, for starters, coral reefs support about 25% of all marine species. They provide homes, food, protection, and they also act as natural barriers protecting our shorelines from erosion of storms, for example. They also contribute billions of dollars to the US economy alone through tourism, defense, fisheries, and along the same lines, they provide food for hundreds of millions of people around the world. Additionally, because they are incredibly sensitive to environmental changes, they end up being critical indicators of both climate change and ocean health. But monitoring coral reefs is actually quite challenging. For starters, they're typically in hard to access locations. So imagine we all decide we want to go to the Great Barrier Reef, for example. We're driving to the airport, we're hopping on a plane, we're driving to the coastline, we're hopping on a boat. That's expensive, time consuming. And so being able to monitor these areas, it's another additive we have to consider. Along the same lines, the data collection itself is actually quite slow and very expensive. The example I like to draw is, imagine we're monitoring a forest, for example. We have a bunch of people, boots on the ground in the forest. We're taking pictures of the trees, measurements. Take that entire operation and shove it under the water. Logistically, things get a lot more complicated. So I've actually included a couple examples on this slide of ways that we traditionally monitor coral reefs, or collect data, if you will. So I have somebody who's swimming, probably taking notes of the different types of corals they're seeing, the amount, somebody with an actual tape measure, measuring these corals. But the one I want you to focus on and pay attention to, because it'll come up later, is this diver who's swimming with a camera rig who's actually taking photos of the seafloor. This will come up a little bit later. But for all of these reasons, it's really difficult for us to monitor corals at large scales. However, there's been a number of advances in coral science over the years, especially using remote sensing. For starters, we've started using both field surveys and remote sensing to do coral reef monitoring. Field methods, as we kind of talked about, provide us with high ecological details, but they're limited spatially and temporally. Remote sensing gives us the ability to do large-scale repeatable reef mapping. And machine learning is a really powerful tool that's starting to be more used to do things like habitat analysis from remote sensing data, for example. And ICESat-2 data, which we haven't talked about yet, but we're going to, and there's a little pencil mark, but that's okay. ICESat-2 data, which we'll talk about a little bit later on, is starting to emerge with capabilities of marine science applications. But there's still some critical gaps in this area. For starters, a lot of reef mapping is both static and single metric, meaning we're focusing on single time points or isolated indicators. We also don't have a way of combining structural, compositional, and bathymetric data all together into one system, so we're typically analyzing these separately. There's also a limited use of integrated and multi-source frameworks, kind of along the same lines. And ICESat-2, which again, we'll get to a little later on, has started to be used for marine applications, but is really underused for its use in coral reef research. So there's this need for integrated, interpretable, and scalable reef monitoring frameworks. I am attacking this gap with the research question of how remote sensing data and machine learning can be used to improve the detection and characterization of coral reef habitats. I'm breaking this up into 3 distinct chapters that kind of build on one another. So detection is really going to focus on this use of ICESat-2 data, machine learning, and how we can integrate those things to detect coral presence. We're going to take a step further. We're going to look at composition, and we're going to look at how remote sensing data can look at mixed composition of corals, capture that. And then we're going to combine those 2 things together, and we're going to build a multi-source remote sensing framework that integrates data and looks at detection and quantifying reef change over time. So before we get too far into it, let's talk about the study site and some data. This is Wistari and Heron Reef, located in the southern tip of the Great Barrier Reef. We have Wistari Reef on the left, Heron Reef on the right, and this like oval situation is Heron Island for reference. I'll use that to kind of orient us a little bit later on. But these are both what we call atoll-style reefs. So we have a really stark perimeter of a coral structure on the outside. The reef edge is usually about 1 meter or 2 deep, depending on the tides, and then it slopes down and outwards to sea. On the inside, where the lagoonal system is, kind of where the sand is, we have like a sand structure, maybe a couple corals throughout. That's usually about 3 to 4 meters deep. But this atoll-style reef gives us the easiest case scenario for being able to detect corals from literally outer space. So just to give you an idea of what we're looking at here, pretend we're jumping on a plane, we're sort of bird's eye viewing, if we could call it that. This photo is taken from Wistari Reef. We can see Heron Reef in the background, and Heron Island for reference here. And what I want you to notice in this photo is how clear and turquoise the water is. And we start to see some kind of coral clusters scattered throughout here. But really, if we want to be able to detect corals, we need to be able to see it visually. And this is a really great start. The second photo is of Heron Reef with Wistari Reef in the background. And again, we can see Heron Island here for reference. And what I want you to notice about this photo is that dark band that goes along the perimeter of the reef. This is our reef edge. So visually, we can see kind of where the reef structure is happening in this photo. To give you an idea of what some of these corals look like, I have staghorn corals on the left and a different clustering of hard corals on the right. When we talk about coral bleaching, which is this idea that the algae that live on the coral, they provide it its color and its food source and protection. And when the waters become inhospitable, this algae will leave, and it will leave corals kind of like a bleached out, washed out color. That's really bad, obviously. They don't exactly die right away, but it does leave them vulnerable. So we're really concerned about bleaching, specifically for these hard corals, because they give us our structure of our reef. So if we start to lose our hard corals, we start to lose the integrity of our reef systems. So ICESat-2, long awaited. ICESat-2 was launched in 2018 for the purpose of monitoring the cryosphere, but it uses a green laser, which means that we can get water penetration. So we actually can end up getting depth measurements, or bathymetry, we often call it. In terms of coverage, we have 6 beams that give us about a 7-kilometer of cross-track coverage. And in the along track direction, we get a measurement about every 70 centimeters or so. And there's about a 91-day repeat cycle. But what's really cool about this data is that it is free and easily accessible, which is huge for building coral reef monitoring products that we want people to use. And I've given you an example of the coverage we have of these tracks. This is 2019 to 2024. Another data set we're going to use is called Planet. And Planet provides us a constellation of satellites, so we get almost near daily coverage. But it's also a high-resolution multispectral image, 3 meters, which is awesome. There are 4 bands that I'm using, blue, green, red, and near infrared. And this photo on the slide is actually one of those photos depicted in real color. This is from August, I think, of 2024, but don't quote me on that. But an example. Additionally, if we're building machine learning models, we need some kind of ground truth data. So this is a data set that we're going to talk about a lot throughout this project. And this is our benthic photo quadrat. So remember that diver with the camera rig taking photos? This is an example of one of those data sets. These 4 images on the bottom are actual images of the seafloor. But what's cool about this data set is that they're also annotated. So not only do I have these photos, but I have the different benthic classes in the photos and the percentage of those classes in the photos. So we're going to use this a lot for training and validating our models. I think I usually talk about this. I call it the photo quadrats. So if you hear me say that, this is what I'm talking about. And the last data set we're going to incorporate is called Allen Coral Atlas. And this was produced by Arizona State University as a global coral reef mapping tool. They use a combination of remote sensing data, in situ data, and some like expert annotations in order to create this. But they give us data products of benthic cover classification, geomorphic zone classification, as well as a depth calculated via satellite-derived bathymetry as well. So we're going to use these data products as well. I've put ground truth in quotes here because when we start mixing in different data sets, what is truth, right? That's a deeper philosophical question for later. But for the sake of the conversation, this is a data set we're going to carry forward to make ground truth. What is truth? So let's talk about chapter 1. So there's a lot more that goes into this workflow than I am going to have time to talk about today. I think I could talk about each of these for an hour. So I'm kind of narrowing down the conversation today. So we're really going to focus on rugosity and slope algorithms, two different classification algorithms, and then we'll look at some results. But if you're interested, this is published in Ecological Informatics, if this isn't enough. But for starters, let's talk about what a coral reef looks like in an ICESat-2 track. So I've included a plotted example of an ICESat-2 track. We're going to break this down together. On our x-axis, we have our UTM northing. This is our along track direction. On our y-axis, we have depth measurement. So basically, we're taking an ICESat-2 track and laying it on its side. That's what we're looking at here. This is an unfiltered track. So the first thing I want you to see is kind of this dense clustering of points that goes all the way across the horizontal of the track. This is our ocean surface. Everything above that is noise. And then underneath, we start to see some different coral features, we'll call them, popping up, and also a lot of noise. So first, and on top, I have a plotted over Wistari Reef. So this particular track is where it's located in real life. So this orange star depicts the bottom of the reef edge. And we can see this popping up as kind of a little dense clustering slopiness of points. We can pop to the top of the reef and look at the other reef edge. And again, we see an even denser clustering of points here. If you can also see, there's a little dense clustering here. That's a little bit of Heron Reef as well, which I think is fun that they both pop in. But then we can look in the middle as well, which is our lagoon, which kind of shows up as like a choppy clustering of points as well. So we can see a clearly defined reef structure in this track, minus all of the noise, of course, which we get rid of. ICESat-2 data in its natural state is essentially XYZ coordinates. So in order to use it for a coral reef related purpose, I've had to be a little creative. And so I've developed two different metrics, rugosity and slope. Rugosity is a surface roughness measurement. So I'm essentially mimicking the way that we calculate rugosity in the field. So if we take this pink line, the way that we calculate rugosity in the field is called the chain and tape method. So we would take a chain, lay it over the topography of the reef, that pink line, that pink L, and we calculate that length. Then we calculate the distance that's covered. That's that black D value. And we're going to take the ratio of those two things, and that gives me some kind of surface roughness. So a value of 1 is perfectly smooth. As it gets larger, indicates more roughness. I'm essentially doing the same exact thing, but I'm taking my ICESat-2 points, which are these little yellow dots, and I'm mimicking rugosity. Did I do that? It's fine. I'm mimicking the rugosity calculation for an ICESat-2 track. We're going to do the same thing with a slope measurement. It's exactly what you think it is. It's a change in elevation. So between my different ICESat-2 points, these yellow dots, I'm calculating the rise over run. I'm going to take these two algorithms and I'm going to calculate them for all of my ICESat-2 tracks for this area. In order to assess that the values I've gotten actually represent what I want them to describe, I've done a qualitative assessment as well. So those photo quadrats we talked about, I'm going to take those and I'm going to geo-reference them with some of my different values. So I've taken a high rugosity, a low rugosity, a high slope, and a low slope. And I can see that the values that I've gotten actually describe the seafloor that I want them to describe, which is awesome. So we're going to carry this data set through the thesis. So I'm going to take those ICESat-2 tracks. I'm also going to interpolate them so I have complete coverage of the surface. I know that these look ugly. They're a little funky. When we imagine interpolation, we imagine a perfectly smooth surface. That's not what we're looking at here. And that's because these are done with Voronoi polygons. They kind of exaggerate the geometric structure of ICESat-2 tracks, if you will. So they look a little funky, but they get the job done. So we're going to carry these particular surfaces later into the chapter. So just like keep these in your brain. let's talk about what the detection model looks like. So as inputs, I'm going to take in a ground truth data set that I am creating. It's in quotes because I'm creating it using a bunch of different data sets. I'm going to use those Allen coral classes that we talked about that were produced by the global reef mapping system. I'm going to take the things that are classified as coral, georeference them with my ICESat-2 tracks so I can identify where coral is on this reef. I'm also going to take those derived metrics we just talked about. I'm going to take the, I'll say, native ICESat-2 variables, so my coordinates. You'll notice there's 2 depth values here. That's because when I extracted bathymetry or depth from my ICESat-2 tracks, I wasn't sure which was more representative of depth, so I just retained them both. And I'm also incorporating that satellite-derived bathymetry metric from the Allen Coral Atlas as well. So we're going to do a little testing and training split, and we're going to train a binary classification model. More on this on the next slide. And from that, we'll get classified subsections of ICESat-2 tracks. But because we have our ground truth data, our validation data, if you will, we're going to evaluate our models, see how they do. We're also going to look at feature analysis. So all of these inputs will be able to analyze how they're performing and which are the most important for which models. More on that later as well. But we can also take this already trained model and take those interpolated surfaces and make predictions for the whole surface as well. So the 2 different models I'm using are a binary classification, binary logistic regression, and a convolutional neural net. The binary logistic regression was really meant as a first pass. Are these variables that we're using to detect corals actually useful? And because the results were pretty good, I went ahead and wrote a convolutional neural network as well. So here's an idea of what that architecture looks like. But we're going to compare the results for these. So I'm using accuracy, F1 score, recall, and false positivity rate. We can see that for all of the metrics, with the exception of recall, the convolutional neural network does outperform the binary logistic regression, as we would expect it to. It's a more complicated system. But let's talk about recall for a second. Recall is the measure of the true positivity rate. So essentially, of all of the possible coral classifications, how many of them did we get right? F1 score is actually a balance of precision and recall, where precision is, of all of the things that you've predicted to be coral, how many of those were right? So for the sake of this argument, the convolutional neural network doesn't do as well in recall, but we're less concerned about recall, right? Because if we were to miss a coral, it's not detrimental. We're not making navigational aids. We're not going to cost anybody billions of dollars by missing a coral, but instead we're erring on the side of not over-predicting coral in this case. I've also included the examples of the convolutional neural network applied to our interpolated surface. So all of the squares in that yellow color are where we've identified there to be coral. So visually, it does a pretty good job. It still has that geometric-like nature to it, but we're okay with that for now. Feature analysis. So we talked a little bit about how we can identify which features are the most impactful for each of the models. For binary logistic regression, these kind of fall right out of the model. We look at the regression coefficients. But for the convolutional neural network, it's a little bit more complicated than that. Oftentimes you hear neural networks described as being black boxes, where we don't really know what's happening underneath the hood. This type of analysis allows us to kind of glance underneath the hood and get an idea of what the model is using the most. So you'll notice they're in different colors, and they also have different axes. Oh, I should also mention that for the convolutional neural network, the way that I'm calculating the feature analysis is using a permutation. So I'm changing the permutations of the inputs and calculating the change in the F1 score. So that's going to be the metric for the convolutional neural network. So different axes, we can't compare them to each other like size-wise, but we can look at the order of the different features. We see that satellite-derived bathymetry is universally the most important variable. But what I want you to see is rugosity and slope. They're not the most important variables, but they are still contributing to both of these models. So we're going to say that they are proxies for benthic habitats. While maybe not the most important, they are contributing, in binary logistic regression more so than the convolutional neural network, but they are contributing. So just to summarize this chapter, I've established a framework for detecting coral reefs using machine learning and ICESat-2. I've created a novel application of ICESat-2 for deriving seafloor structural metrics. I found that SDB, or depth, was the most dominant predictor of reef presence. And I've also established a foundational framework for scalable, cost-effective reef monitoring. And again, if you didn't get enough, this is published in Ecological Informatics. Let's talk about chapter 2, composition. I've included a workflow for this as well. So really what we're doing here is benthic composition using spectral imagery. So I've done this in 3 different ways, 3 different models, this green color here. The first way, or the first 2 ways, are both machine learning methods. And what's unique about the machine learning methods is that we get discrete class outputs from both of these. So I'm using a k-means clustering and an AdaBoost decision tree. We're not going to talk about those today, but they're there. But the discrete class outputs are very different than what we get out of an optimization-based approach, which gives us actually fractional coverage. So for every pixel, we can actually tell the fraction of each of the benthic classes in that pixel. So we're going to focus on that habitat map today. We're going to focus on spectral and mixing because I think it's cooler, among other reasons. But again, it's published in Remote Sensing if you need more information. So linear spectral and mixing allows us to decompose all of our pixels into a linear combination of the benthic classes in that photo. So just to kind of walk you through how this works, I'm taking this super realistic image of the seafloor. Bear with me. We have land in the top left-hand corner. We have some water, deep water on the right. These colorful corals are our live corals. The bleached out corals here are our dead corals. And then there's kind of that sandy color in the middle. So if we take one of these pixels, spectral and mixing allows us to create something that looks a little bit like this. So in this case, end member refers to our different benthic classes: dead coral, live coral, water, sand, land. And abundances is that fractional coverage of that class in the pixel. Mathematically, we would represent this with something that looks a little bit like this. So in this case, X is going to be our raster image. It's composed of spectral bands and pixels. I'm going to skip S for a second, but A is our abundance matrix. So a matrix of these different values we just derived. And S is a spectral library, which is going to have a spectral value associated with each benthic class. Let's think of it as kind of a ground truth data, but it's not really that. Maybe that made it confusing, but spectral library, just keep that in your brain for now. But because using spectral and mixing for benthic composition is more of a novel approach, we run into 2 different problems. The first problem is that linear models are unrealistic in an optically complex environment like that of a coral reef. It's a simpler problem to solve, but it doesn't take into consideration the nonlinear dynamics that we know happen between the different spectral classes and the benthic classes, spectral bands and benthic classes. The other problem is that we need some kind of spectral library. Oftentimes these are measured in the field. We don't have that information. We can kind of solve for one instead of a predefined one. And that might look a little bit something like this. We're going to zoom in on this in a minute. But essentially the way that this is created is if we take each of our photo quadrats and georeference them with the raster image underneath, I can take that fractional coverage we have the benthic classes and the percent cover, and I can add the spectral bands to them. So I can kind of create a ground truth data set, if you will. But this presents other problems. Let's zoom in. So on the x-axis, I have my 4 spectral bands, and on my y-axis, I have the mean spectral reflectance. So essentially what I've done is I've created the ground truth data set, and I've averaged the spectral value associated with each of these classes. But when you look at this, or I should also say that each of the lines is a different benthic class. But when you look at this, you'll notice that the yellow and the turquoise are almost indistinguishable from each other. This is our sand and our live coral. So if in our ground truth data set, we can't tell the difference between 2 of our classes, it's going to be almost impossible for us to be able to distinguish them from a super complex pixel that the model hasn't looked at yet. So we're combating this in 2 different ways. The first way is we're actually going to boost up that input data set. So inspired by what we do in remote sensing a lot, we use traditional indices. So like the normalized mean difference water index or the normalized mean difference vegetation index. The vegetation index, for example, looks at the near infrared band and the red band and uses that to better identify vegetation. Rather than picking 2 bands, I'm actually going to use all of the bands, but I'm going to calculate band ratios and normalize band differences. So our input data is going from 4 inputs to 16 inputs. I'm getting 12 from these. So first thing we're doing. The second thing we're doing is in the way that we're formulating the framework to unmix. So this is actually solving an optimization problem within an optimization problem. So we're going to take that ground truth data, just like we described it with the photo quadrats geo-referenced with the image underneath, except now our inputs are all 16 of those bands, the original 4 bands and the derived spectral features, and those abundances that are associated with each of the photo quadrats. We're going to use that to solve for S. We're going to take that S and we're going to shove it into a solution for A using the remainder of the spectral image, and from there we'll get a benthic composition map. So we're going to solve for S as the weighted mean of the ground truth pixels. So S is the spectral library we're solving for. A are those abundances we have from the ground truth. X is a collection of different spectral information. There's 16 of them. And we're going to solve for S as kind of a back solve. We're going to solve the inverse of the linear mix problem. And we can do this by solving for using the least squares method, where we're basically taking our observed value and a recreated value, if you will, A transpose S, and we're going to minimize the difference between those two things with respect to S. We're going to take that S and we're going to shove it into a solution, a nonlinear framework for A. This one looks a lot more complicated, I know, but none of our indices have changed, okay? So instead of the ground truth data, we're using the rest of our spectral image. So A is the abundances we're trying to solve for. X is going to be our input features. Remember, there's 16 of them now, and S we just solved for. So this is formulated by actually looking at 2 individual pixels at the same time. And this takes into consideration the nonlinear dynamics we know are happening between the benthic abundances and the different benthic classes. Okay, so we're taking into consideration the fact that oftentimes we have 2 pixels that have the same exact spectral value, but are sometimes labeled differently. So this formulation ends up being more robust to environmental variability because of the ratio-based method of it, if you will. I'm also imposing some constraints on this as well. So all of our members of A must be between 0 and 1, meaning we're not going to have any negative contributions of benthic classes. And A has to sum to 1, meaning for every pixel, we'll have 100% coverage at the end of the day. And we're going to minimize with respect to A using the sequential least squares method. And the fun part is the actual results. So what we're looking at here, each of these plots represents a different benthic class. Pixels that are in that bright yellow color are 100% coverage. I think land is probably the best example of this. And pixels in that dark purpley color are 0% coverage. But what's more interesting is every single pixel that falls in between that spectrum. These are our mixed pixels. So we're actually able to capture a mix of each of these different classes on our study site. And while this representation is more ecologically realistic, in order to use it downstream, I've also discretized this. So I've taken those 5 maps and I've chosen the most abundant end member to represent each pixel. So now I have 1 map at the end of the day. And so I am comparing these different classes using F1 scores. So really all you need to know is that 0 is bad and 1 is good. It's a balance between precision and recall. So we see it does a pretty good job in most of the classes, with the exception of live coral. But if you'll draw your eyes to the left picture, the plot itself, we can see there's actually a lot of live coral being presented. And so we know that this method is actually capturing the patchiness of the reef, despite the fact that we have a lower F1 score. And the lower F1 score is because we only have about 12% of the ground truth data representing this live coral classification. But we're going to retain this discretized map for use later down the line. So just keep that in your brain. And so just to summarize, I've created a novel nonlinear spectral unmixing approach for benthic composition mapping by integrating field data and satellite imagery into a single classification framework. We found that ground truth data was the primary constraint, not necessarily the model. And ultimately, unmixing allows us to capture sub-pixel habitat composition and fine-scale benthic heterogeneity that it would have been missed by our machine learning classifiers. And again, if you want more information, this is published in Remote Sensing. So let's talk about the last and final chapter. So if you've been following along, you know that we've already talked about slope and rugosity extraction as well as those reefs, those interpolated surfaces. And we just finished talking about spectral unmixing. I'm adding in another variable here called satellite derived bathymetry, different from alien coral outlets. We'll talk about that in a second. And ultimately, I'm creating a change detection model that composes all of these different metrics we just talked about together. And this manuscript is under review, but available if you're interested. So in order to choose a time frame where we're detecting change, we need to know that some kind of change occurred. So we're looking between 2020 and 2025 because there were a number of different disturbance events. For starters, we talked about the 3 out of the 4 mass bleaching events that have ever occurred happening between 2020 and now. So we see there are 3 mass bleaching events. There are a number of different cyclones of different categories that have happened in this time frame. And we can also see marine heat waves every single year at least once. So this is a really good time period for us to look for there to be change. So I'm building a multimetric change detection framework that integrates structural, compositional, and bathymetric metrics. Rugosity, we're going to take from that first chapter. We're going to calculate for tracks from 2020, tracks from 2025, and we'll create surfaces of these. Same thing with slope, same tracks, different value. And we're going to take the spectral unmixing results and derive coral cover from those products. And then we're adding in a depth variable as well. And so I've taken my satellite image and my ICESat-2 depths, and I've used a random forest to create a depth map for you, if you will. Not for you, for me, but a depth map, if you will. And so I'm going to take these 4 metrics, and I'm going to put them together and create change detection surfaces. So this is essentially a subtraction, 2020 from 2025, to look at how much change occurred. But each of these surfaces are filtered using an individually defined threshold value that determines how much change needs to occur in order for it to be detectable. So any of these pixels that are in white are undetected change. Pixels in yellow are increased values, and pixels in that dark blue color are decreased values. And so we start to see some different spatial patterns coming through when we look at this. But if we take this a step further, we can actually apply a Moran's-eye hotspot analysis to do some autocorrelation detection as well. So I've taken these surfaces, I've interpolated them to 100 meters, and this is because I'm not concerned about fine scale changes. I want a global idea of change across this reef. So each of these dots represents a 100-meter area, 100-meter square area. Dots that are in that red color are going to be increased clusters, so increased values surrounded by other increased values. The HH means high, high, so high values, high clusters. The blue values are going to be decreased clusters, so decreased values surrounded by other decreased values. And that pink and teal color are outliers. We're not really concerned about that. So we can see even more spatial patterns kind of popping through with this analysis. But I've also overlaid all of these hotspots onto a geomorphic map to get an idea of which geomorphic classes are experiencing the most amount of change. But you'll notice that the change is not uniform across all of these classes. For example, if we look at this yellow box at the northern tip of the reef, it's a little bit of reef extent, but it's mostly reef crest. So for rugosity, we're seeing major decreased values in rugosity. For slope, we're seeing some increases, some little outliers. For depth, we're seeing an increase in depth, which means it's getting deeper. And for coral, there's kind of a mix of there's some decreased coral, there's some increased. But if we take another example, also on the reef crest, this green square, we can see there's not really much happening in depth, not really much happening in slope, but we see a lot of increases in rugosity, and we see some increases in coral cover. So these are 2 different examples happening on the reef crest where the change is not the same in both of these areas. So additionally, I've taken each of these products and I've also combined them into one product so we can get an idea of change under one metric. And this is our composite change index. And I'm calculating a weighted sum of normalized autocorrelation of change values. So let me break that down. The Z value in this equation is going to be our normalized local Moran's-eye values for each change metric. I've also taken the absolute value of these, so we're not concerned if the change was an increase or a decrease, we're just concerned about the magnitude of that change. And I'm weighting those values based on the statistical significance of the hotspot. So part of the Moran's-eye analysis, we get p-values for the confidence of each of those Moran's-eye values. So I'm using a 95% confidence. If a pixel or a hotspot was statistically significant, I'm giving it a weight of 2. If it was not, I'm just giving it a weight of 1. So we're putting more emphasis on our hotspots that were statistically significant. I've also analyzed those top change values just to get an idea of where they're happening. We see that there's a lot of change happening in the reef extent and the reef crest. The reef crest kind of makes sense because it takes up the majority of our reef, but the reef extent is noteworthy for sure. But what's also interesting is deep lagoon seems to be a really stable area. We could argue that reef slope and the shallow lagoon are also really stable areas as well. But as we saw on the hotspots change side, we can't just look at this plot by itself because this change is not uniform across the reef. So we can actually take a closer look at which spots are changing spatially in order to highlight areas of concern. Let's take a zoomed in on this product as well, because I think this product is where this work really shines. This product shows that we're able to pinpoint areas of change. So where this product may be used is I would go to a diving team or a management team for Heron Island specifically, and I would say, you really need to take another look at what's happening on this northern side of the reef. There seems to be a lot of influx, also on this western side as well, but there's not really a lot happening on the eastern side for whatever reason. So maybe collect some more ground truth data. We can guide them to prioritize where they're collecting more data. We can also help them make management decisions based on information like this. And overall, we talked about how expensive it was to monitor reefs, but I did all of this from my little desk in New Hampshire. So we're ultimately reducing monitoring costs as a whole as well. So just to summarize this chapter, I've developed a multi-source framework for detecting coral reef change over time. I've integrated structural, compositional, and bathymetric metrics into a unified workflow. I've also revealed heterogeneous change patterns that would have been missed if we only looked at each of those metrics individually. And overall, I've demonstrated a scalable, data-driven approach for coral reef monitoring and decision support. And it's a work in progress, hopefully published soon as well, but available upon request if interested. And just to kind of tie the whole chapter, the whole thesis into a beautiful bow, this work integrates ICESat-2 data, imagery, and field observations into a unified workflow. I've extended the use of ICESat-2 beyond just depth retrievals to actually derive ecologically meaningful reef structure metrics. I've also combined structural, compositional, and bathymetric information into a single analysis framework. And ultimately, I've advanced static mapping to more integrated reef detection. And what do I want you to take away? Why is this useful? We've introduced scalable multi-source framework for coral reef change detection. Ultimately, this work really aims to support early decision-making. So if we were to have a cyclone, for example, we could take information before the event, after the event, and get almost real-time change of what happened due to this event. We also are able to prioritize areas that need targeted management or more field validation. And ultimately, we've enabled large-scale, cost-effective, and continuous monitoring. So here are some references. And now time for my Oscars speech. I'm half joking, but I am soft and sentimental and squishy, and so I can't defend my dissertation and not say all of this. They say that you do the most amount of growth when you are in uncomfortable or difficult situations. And what is more uncomfortable and difficult than doing a PhD? So to visualize growth, my Monstera, if you know me, you know I love my plants. We moved here together in 2021, as well as Tyler. And not to be second after that, over the 5 years, I have had the opportunity to grow into my beautiful pride and joy, my Monstera. But this is all in part due to the wonderful and amazing humans that I am so lucky to be surrounded by. I have to start with my advisors, of course, Kim. I had a very specific idea of what I thought an advisor should look like when I started my PhD, and you have blown all of my expectations out of the water. I genuinely don't think that this project would be as cool as it is if it wasn't for you. So thank you for everything that you've taught me, from how to be a good researcher to how to do life. I think that you are a grade A awesome advisor. So thank you. Mark, you really made sure that this thesis at the end of the day was applied math. So thank you for that. And I had so much fun collaborating with you on the unmixing method. I don't think it would be as cool as it is if it wasn't for you. So I appreciate you as well. And all of your mentorship over the years too. And to the rest of my committee, I have Jen and Merrick, and Chris is online with us, joining us from Oregon. thank you for going on this journey with me, for being insightful and having great advice to give at any turn. Jen, this wouldn't be coral if it wasn't for you. So thank you for answering my silly questions like, is this one a coral? I've also really enjoyed collaborating with you on all of these projects. I've listed a whole bunch of people from CCOM and IM. I don't think it's an exhaustive list, but these are all the people, and oh, I just hit my step goal. These are all of the people who have been so impactful in me being able to complete this thesis and my classes, and I'm so grateful for all of you. You know who you are, you know what you did. I also need to mention my undergraduate community and my mentors, Dr. Julian Flaron, who I think is online. He is the reason that I decided to study math. He saw the potential in me and has offered me mentorship even today, and I am so grateful for you. And Dr. Borwerk, she showed me what research was my senior year of college, and I have been hooked ever since, so shout out. Thank you to all of my friends here and online, and my family. My mom and dad and Danielle and my aunt are here, and I'm not going to look at any of you because I'll start crying. Everything that I have accomplished up until this point is because of you guys. So thank you for teaching me the love of learning at a young age, because I love to learn and this wouldn't exist without you. And Danielle, shout out, she's an accomplished queen in her own right. Thank you for being my best friend. Fernando, he is this furry, cute boy all over the slide. He's perfect, no notes. And Tyler, I can't put into words how much you have helped me over the years. Thank you for moving to New Hampshire with me 5 years ago and maybe moving somewhere crazy again. Love you. Doesn't feel like enough, but yeah, great. And also, thank you for all of you for being here today. And with that, I'll take your questions.
And I will let Natalie manage the questions.
Natalie, take it away.
Yeah.
Yes, I will take the questions. Yes, Yuri.
Yeah, I have a question about, you mentioned that CNN outperforms linear regression, right?
In my regression?
Linear.
Oh, in the detection, yes.
Yeah, in the detection. And I noticed that in CNN, rugosity and slope are the least important features.
Correct.
So, of course, any feature that you would include there would contribute in some way.
I agree.
But these are contributing so little. Why do you care about them?
We care about them because I think that they are proxies in their own right. And I think that
are important, yes.
Agreed.
If they are so little of little importance, then why?
I would argue that the convolutional neural network shows that they're of little importance, but we're also analyzing the binary logistic regression as well, and they have more importance in that model than they do in the convolutional neural network. So I'm not taking just the convolutional neural network, despite the fact that it did better, but I'm actually erring on the side of the binary logistic regression has pre-established ways that we can monitor those features or get an idea of how important they are. So I've retained them because they actually do show importance in the binary logistic regression as well. And I also think there's other ways that we probably could have analyzed them in the convolutional neural network. That was just the way that I chose to do so. But we could measure change in recall, change in precision, among other things. But great question. Thank you. Larry.
This may be a crazy question, but do you have a place where you've measured depth or included depth in the analysis that was not derived from satellite derived bathymetry?
Well, would you consider ICESat-2 as depth? Then in that case, yes. Do I have a ground truth measurement of depth? No. But I am also using ICESat-2 depth values.
And it was always the satellite derived bathymetry depth that showed the best predictive capability.
Yeah.
As opposed to the ICESat-2 depth.
Yeah.
And I don't know, when you had mean and median depths, they were worthless in a sense in terms of a predictor, but I'm not sure what they were. the mean and median of. Is it possible, due to the nature of satellite derived bathymetry, that there's a bias in satellite derived bathymetry because it's actually reflectivity measure of some sort of the seafloor? So is it potentially a bias in there that is making it much more sensitive to the presence or absence of coral?
There might be, and I think that satellite derived bathymetry is one of those variables that not explicitly has correlations with other variables, but we think about like water attenuation, or there's often a correlation between different depth values and different benthic habitats. So I do think that satellite derived bathymetry variable has the potential to have also incorporated all of those things, whether consciously or subconsciously as well. I think that's a great point. Yeah, thank you. Owen.
We got a couple of questions from online. Kevin, a whole bunch of people giving you congratulations and saying great job, your star.
Thanks, guys.
Kevin Short says, Gabby, nice job. Question, in the neural network, what activation function and optimizer did you use? I may have missed the diagram.
I'm using an RELU function. I can go back. One sec. I can't talk and do this at the same time. I'm using an RELU activation function at the end. And what was the other question? The optimization. The optimizer is an Adams optimizer. That's the optimizer I used. Do that. Yeah. It doesn't say it on the slide.
I also have more questions on
Hold on, wait.
Give somebody in the room.
Adriana.
Yeah, first of all, that was awesome. And based on the last presentation you gave to now, it's crazy that it got better, but it did. So, yeah, that was really awesome.
Adriana was subjected to it last week. Among
well, one of my questions was Yuri's question, so I'm going to skip that one. How did you decide the change thresholds that you considered significant? Is there and as a follow-up question.
Wait, hold on. Can I answer one at a time?
Yeah, you can. It's kind of together. But.
Great, fantastic. This is one of my extra slides. So it's a little ugly. I apologize, it doesn't have the proper pizzazz. But the individual thresholds are defined by using the special law of propagation of variances. And so through this calculation, I'm assuming that the uncertainty is equal at both times. And I'm actually calculating that propagated error as the 10% of the observed max. And so these are the values on my right-hand side that I'm actually using to define the thresholds. I also did a little bit of comparative. I created a histogram for each of these variables. They were about normally distributed. So each of these values are either comparable to what the STD standard deviation would be, if not like a little bit more conservative, just to err on the side of caution. But great question.
Right.
Thanks for letting me go to my.
Well, yeah, I also want to say
yeah.
it's not a plant question. I didn't know she had a slide ready for this. And yeah, for when you talked about the Morin's eye, your correlation, how did you decide what was the high weight again? Is it what you gave the weight of 2 for calculation?
Oh,
is that like a clustering thing, or is it?
Yeah.
Okay.
It's a p-value that pops out of the clustering algorithm. Each of these values has a Morin's eye value associated with it, and there's a p-value that comes from it as well. And you're talking more so about this slide, I think, of the weight value that's assigned. Yeah, so the statistical significance comes out of the calculation of the Morin's eye. Good question. Yeah.
I was wondering, the whole talk was kind of viewed through the lens of these specific reefs.
Mm-hmm.
Why did you pick those? Were they like reefs with extensive in situ observations, or were they just like particularly illuminating for the type of analysis you're doing?
Maybe all of the above. I really chose these reefs because of their atoll style structure, which makes them the easiest case scenario for being able to detect reefs from space. They also have really good historic data. It's not as good as a machine learning person would love it to be. For example, I think you can really see on this slide, all of these yellow dots on the screen are where I have historic data or in situ data, but it's not complete coverage. But this is a lot better than most of the reefs because again, collecting data is really expensive. So I think the next, not that you asked, but I'm going to say, the next part of this research is really to apply these methods onto different types of reef systems in different ocean basins in different areas and fully test that geographic robustness, if you will. Thank you. Good question. John Kelly.
Gabby, go to some of your final slides, the third from the last.
My second to last. We're going to start here. And you're going to tell me if we're close.
Keep going, right towards the end of your talk.
We're at the end.
No, keep going. Before your Oscar.
Oh, good call. Other direction.
Yeah. Nope, one back up. Right there. Oh. Okay, just take that.
Next one? This one? Okay.
No, you skipped it.
Oh my gosh.
Keep going, one more back.
Back or forward? Okay.
All right. That number 2 bullet,
Yeah.
support early detection of stress events, reef change. As you probably know, NOAA does their coral reef outlook, the satellite service specifically. So I was wondering where you think your research would be useful for NOAA, the satellite service, to use in their bleaching outlooks and all the different other forecast products.
Yeah, that's a great question. I think that when it comes to using machine learning models, we would really benefit from looking at all of the models together. I think that there's the potential that some models are better at some things and other models are better at other things. So I think the best way to get an awesome prediction of coral future predictability or current predictability even would be to combine as many as we can into some kind of system. So I could see this fitting in quite nicely with being able to get an idea of how much change occurred because of events or, but I really think that it serves as a complement best because, yeah.
So you could use it for verification.
Yeah, absolutely.
And see whether actually it was the worst case if it actually occurred.
Yeah, absolutely.
Okay,
Cool.
thanks.
Yeah.
So if you were tasked with gathering more in situ data for this study site, where would you do that?
I would do it. We're just going to pop back here for a second. First of all, I think it would be really helpful if we could literally repeat these same exact spaces because this data set is from 2018. So if we had the same or as close as we can to the same exact locations for a future date, I think that emphasizes the detection because we'll have actual ground truth validation of change. But I would also say, let's get everywhere else on the reef, right? Because when we look at the final composite change index, you'll notice that most of the change we see, forgot my clicker. Most of the change we see is concentrated on this left-hand side, right? But on the right-hand side, we don't have a lot of change in that composite change value, but we also don't have a lot of in situ data as well. So I think trying to get a balance across the whole site geographically would be really beneficial too. And to increase live coral. That was a big one too. Yeah, great question. Should I pop to online?
Sure. You've sort of touched on one of these and the other one Chris Parrish just responded to. Robert Young said, I volunteer for a foundation in the Bahamas and I'm trying to up their monitoring game. The reef we're focusing on goes from less than 3 meters in depth to close to 50 meters. Will ICESat-2 handle it? And Chris said, Bahamas contains some of the deepest ICESat-2 bathymetry I've ever seen, but 50 meters is probably a bit of a stretch. 40 meters seems to be more of the limit on that.
Yeah.
And the second part of Robert's question was, how would additional ground truth data contribute to your analysis?
Oh, I think it would improve results. I think we would have a better classification across all of our classes if we had more results, and that it would just strengthen the accuracy of our models. But great question. Dad.
For us non-CCOM people, what organization or company controls the ICESat data, and how often are they actually?
So ICESat is constantly capturing data. It's controlled by NASA. Kim's nodding, so NASA. The thing that I actually just recently learned about ICESat-2 data is it was launched in 2018 and it's been about 7 years. And they gave it 7 years worth of fuel. So it's still going. She's still collecting data, but for how long, I guess I'm not really sure. Chris might be a better expert in that domain. But it is constantly collecting data as it circulates through the Earth.
So you could run this every day and get a different.
I just realized I can unmute myself. Do you want me to answer that, Gabby? Or contribute to that answer?
Hold on, let me turn my sound up, Chris. Okay, go ahead.
Sorry, if you wanted me to, I can contribute to that answer. I think ICESat-2 has enough mission resources for about another 8 years of operations. So that's fuel, for example, but it also depends on if the mission continues to receive support for continuing operations. But yeah, you're right. The prime mission is already well over, and we're into the bonus period now.
Chris, I'm so sorry to say that our sound is all the way up, and I don't know if anyone heard that. But I really appreciate your answer.
I'll put it in the
And
chat.
I'll just clarify, the repeat cycle is 91 days. So ICESat will go over every 91 days. So when you say, well, can you do this every day? No,
No.
every 91 days if it's cloud free.
Great, thank you. Sorry, Chris. I'll let you know later. Natalie?
Since we're on the slide, do you know why they chose those sections for the photo transects?
I don't know explicitly why. This particular data set has a couple different years of coverage. So I would assume that either they're trying to get the same data or they're trying to get more data in different areas, but I'm not entirely sure why they chose what they did. I wasn't there. Juliet?
Good job, Gabby. So you said that a lot of the data is from 2018 or earlier. Were you able to get any of your 3 studies get aerial satellite imagery corresponding to when those data were sent?
Yes. So for the first 2 chapters, all of the data correlates with this 2018 timeframe. But for the 3rd chapter, the data all correlates with either a 2020 timeframe or a 2025, but December of 2024. So they're all within a month of each other. The way that the data is correlated. ICESat-2 might be a little different. That might be more like 3 months, but they're all within the same year. Yeah, good question.
We move on to this slide. We have the CNN and the other information.
You want to see the architecture?
Correct.
And Chris just wrote out, there's enough mission resources, e.g. fuel for another 8 years, assuming support for the mission extension.
Cool. 8 more years. Thanks, Chris. Cool. Is this the slide?
The other one that has the slope rugosity, like the one that has the CNN and the other.
The results?
We go one more.
Correct.
Okay, cool.
So I'm thinking in learning AI, they tend to do better with photometric properties.
Okay.
Given that most of your modeling is like geometric heavy and satellite derived bathymetry, would you think that's why the VLR does better than the CNN?
Maybe. That could be part of it. Honestly, that's an interesting perspective. I hadn't thought of that. That could be part of it. I think it also, the binary logistic regression does a more natural job of feature importance. So I think that's part of the, I guess I don't really know. That's a good question. Yeah. Adriana, do you have a?
Yeah, could it be that the CNN is finding its own proxies for rugosity and slope, and that's why it's not using it?
100%.
Whereas the VLR is just straight.
Yeah, oftentimes neural networks detect features that we can't put words to. So that could be part of the rugosity and slope do a less good job, if you will, because it's actually learning something that is maybe a combination of all of these things and there's no label to it. But yeah, that's a great point.
I think we'll take one more question and then we'll wrap up. So if anyone has one last question.
Matt.
So the spectral unmixing, I imagine that is a computationally expensive process, right? Like just out of curiosity, like how expensive? Like how long is that?
She's running on a supercomputer
Yeah.
on premise. Yeah, it takes a couple hours. And I have done a lot of training, or not training, but testing with just a smaller study site. That's part of the reason why the spectral unmixing, you only see Heron Reef, you don't see Heron and Twistari Reef, is because it takes hours to run. Yeah.
Do you have any like computational scalability? Like if you parallelized or?
Oh yeah, she's parallelized, she's on premise. I did all of it.
Thank you.
Yeah, absolutely.
All right, well, thank you all for being here. Committee members, as I said, we will go up to the Admiral's Conference Room. Chris, I think there's a Zoom link specifically for you to tie in there. Rest assured, we won't start without you. But anyway, thank you all, and thank you, Gabby, for the presentation.
Thank you.